Okay, we're going to try that again. I'm going to run through all of the answers here to heat worksheet number 1 that was assigned on Thursday, March 26th, chemistry kids. So if equal masses of liquid water, dry air, granite, and lead are heated to 100 degrees, which would cool at the slowest rate. So we look at these specific heats: granite, air, and lead. And remember what the specific heat is. And I didn't write water because I'm assuming that from the notes you recall that the specific heat of water, CH2O, is 4.18 joules per gram degrees Celsius. And if we go ahead and we think about this, specific heat tells you how much heat is required to change 1 gram of substance by 1 degree Celsius. So granite only requires 0.78 joules of energy. Air requires a little bit more energy. Lead requires very little energy to change 1 gram of it by 1 degree Celsius, and water requires a huge amount of energy. So which one's going to cool slowest is going to be the one that requires the most amount of energy to change its temperature. So I would say that water will cool the slowest because it has the largest specific heat. So if I flip that question around and I said, who cools the fastest, I'd be looking for the one that has the lowest specific heat because it requires the absolute least amount of energy to change each gram of substance by 1 degree Celsius. So the one that would cool the fastest here would be lead. All right, let's go ahead and look at question number 2. It says, let's go ahead and draw a picture, excuse me. Describes the flow of energy when a 3-gram piece of hot iron is dropped into a 25 degrees Celsius bucket of water. All right, so let's think about what that might look like. So here, and I'll go ahead and scooch this up just a little bit. So here's my bucket, and here is my water. And so here is my little 3-gram chunk of hot iron. And so the heat that hot iron has, the heat is going to be flowing out into the water. So if I put and label those as Q's, because remember Q is the symbol for heat, which is just thermal energy, and we measure that in joules. So that would represent a little picture there. All right, part B, it says draw a molecular level picture that describes the changes occurring in the motion of the molecules in each substance as the energy is being transferred. So you could literally think about the molecules of that hot iron, which originally are, they're really, really vibrating and wiggling and moving, and there's a lot of motion in the hot iron. And then as you think about as it cools, there's going to be less motion. So there's going to be less moving about. All right, so less motion in cooling iron. Now, simultaneously, what would we expect to see at a molecular level for the water molecules? So here's my water molecule, H2O, and maybe at first it was moving with that amount of velocity. Now it gains some energy. So what's going to happen is that water molecule is going to now be flying around, banging into each other with a lot higher velocity, okay? And then how would this change in molecular motion translate into changes in temperature? So if we think about it, we now know that the iron is wiggling a little bit less. It's got less energy, so the temperature is going to drop for the iron, which makes sense because it's sitting in the colder water. And we know that the temperature is going to rise for the water. All right, so that's number 2. All right, and now we get into really the problems. And let's go ahead and see how many of these we can get solved here. So number 3, let's calculate the specific heat of mercury metal. All right, if 250 grams of the metal goes from, and you're just like, oh my gosh, there's so many numbers. So just keep it straight. We know that Q is equal to MC delta T. And I'm gonna make that just a tiny bit bigger, I think. All right, there we go. So Q is equal to MC delta T. And let's think about what we know. We know that we've got 250 grams of our substance, so that's my mass. We know that it is absorbing 607 joules of heat. So if it's absorbing heat, it makes sense that the temperature is going up. So that is a gain of energy. So it's 607 joules worth of heat, 607 joules worth of energy. Sorry for the autofocus there on my camera. And then we don't know the specific heat C, but we remember that delta T, the change in temperature, is the final temperature, 37.4 degrees Celsius minus 20.2. Oops, 20.2 degrees Celsius. So delta T, 37, 27, 17. I want to say that that's 17.2 degrees Celsius. And I'm just going to hope that I'm doing that math right in my head. I'm going to go ahead then and do a little bit of mathing on my calculator. So bear with me for just a second. And so at this point, I'm going to take 607 and I'm going to divide it by 250. And then I'm going to divide it again by 17.2. And so if I've done my math right, you end up with 0.141, and I'm going to take it out to 3 sig figs because I'm going to assume that everything here is, well, that's 4, 3, I'm going to go 3 sig figs, 0.141. And the units, you can actually see it. It's joules divided by grams divided by degrees Celsius. And so that would be your answer for the specific heat of mercury. All right, let's go ahead and tackle number 4. And I'm going to go ahead and fold this just so that we have a little less distraction there. And so we've got our mercury metal. It's absorbing some heat here. It's going from 25.5 to 52.5 degrees Celsius. It's giving us how much heat is absorbed, and it's asking me for the mass of mercury, and it's giving us the specific heat. So again, Q is equal to mc delta T. We look at what we know, and what we know is that the amount of heat absorbed is 782, not grams, joules worth of energy. And we don't know the mass, so we go ahead and go M. And then we say, all right, what is the specific heat? We know it, it's 0.14 joules per gram degrees Celsius. And then we're gonna say, all right, what is the change in temperature? Change in temperature is final minus initial. It went from 25.5 up to 52.5, so the final temperature is 52.5. The initial temperature is 25.5, and so I'm getting a delta T, and I got to go out to my calculator here because this one I'm not gonna do right in my head. I'm convinced 52.5 minus 25.5. Oh, well, I should have been able to do that in my head. 27 degrees Celsius. Mr. Caldwell needs some coffee. So we gained heat to the tune of 782 joules worth of energy, and that gain of heat caused a change of 27 degrees Celsius of rise. That's why it's a positive number. So at this point, we go ahead and just do the math. We're going to divide the 782. 782 divided by 0.14, and then we're going to divide that by 27. And I'm getting an answer, and I'm going to look at my sig figs. I've got 3 sig figs, 3 sig figs, 3. I've got 2, so I'm going to go to 2 sig figs. I'm going to say 206, which would go to 210 grams. Okay, so that is number 4. All right, and I'm going to go ahead and pause this video here. I'm going to break this up into 2 sections. So this is, well, no, you know what? I'm going to keep going, I think. Nope, we're going to keep going. And let's go ahead and do number 5. All right, block of aluminum, 140 grams, cooled from 98.4 to 62.2. All right, and we know that it releases heat. So now we're getting something that, let's see here, number 5, I'm sorry, I couldn't see it on my screen. And again, we think Q equals mc delta T. Since I'm releasing heat, I'm giving it off. That is a loss. So I'm going to put a negative sign out here, 4519. And that is the amount of energy associated with that. We don't know the mass, or we do. We do know the mass. It's 140 grams. We don't know the specific heat of aluminum. That's what we're trying to solve for. Like, how much energy does it take to change 1 gram of aluminum by 1 degree Celsius? And then we look at the delta T. We know that delta T here, it went from 98.4 to 62.2. So the final temperature was 62.2. We always do final minus initial, minus 98.4 degrees Celsius. So delta T is equal to, and again, I'm going to my calculator just because I'm old and feeble, 62.2 minus 98.4. I've got a loss minus 36.2 degrees Celsius. So I'm going to go with minus 36.2, and the rest of it is just math. So we're going to go ahead and say, let's take, and you'll see that the negative signs are going to cancel out, which is good. C is always a positive quantity. 4519 divided by 140 divided by 36.2. And I'm looking at this, and I'm actually seeing only 2 sig figs in that 140 grams. So I'm going to go to 2 sig figs in my answer and go with 0.89 joules per gram degree Celsius. And that, my friends, would be the answer to number 5. All right, moving right along here, doing great. Number 6. Okay, cube of gold, and we know the mass. We know it's going from 30 to some higher temperature. And so the challenge in these problems is really looking at them, deciding what information we have, and then just choosing the correct, I got too many things on here, I'm trying to save paper, and just trying to keep everything straight. So we know Q equals MC delta T. As we work our way from left to right, it's absorbing 945 joules worth of energy, so it gains 945, so that's positive. We know that the mass is 192.4 grams. We know that the specific heat is 0.126 joules per gram degree Celsius. And we then think, remember, delta T is final temperature minus initial temperature. Now in this case, it's asking me for the final temperature. And what I don't know is what I'm asked for is the final. What I do know is that it started out at 30 degrees Celsius. So this ends up being the math problem that we have to do. And so at this point, we just do some calculator stuff, and I'm going to go 192.4 times 0.126. And so that's 24.2424. So I've got 945 equals 24.2424. And I'm going to just distribute that through. So that's times the TF. And then when I take that and I multiply it by 30, that gives me, and remember, it's going to be a positive quantity times a negative. So I'm going with a negative 727.272. And now we just take that guy, add it to the 945, and then we're going to divide, that's 1672.272, divide that by the 24.2424. Nothing more exciting than listening to Mr. Caldwell do some math. Sorry about that. So unless I've really screwed up my math on the calculator, I'm getting, let me double check. I see 4 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So I'm going 3 sig figs. I'm going 68.98. So I'm going 69.0. And that would be a temperature. That would be degrees Celsius. All right. Oh, man. And now we are at the last one. Question number 7. Let's see if we can get that one done. So we have a total of 226 joules of heat are absorbed as we've got a mass of lead, and we know that it's being heated from 12 to 42. So away we go. Q equals MC delta T. We know that it's absorbing, so it's gaining 226 joules worth of energy. We know that the mass is 58.3 grams. We don't know the specific heat, but we do know that delta T is final minus initial. And so the final temperature is 42, the initial is 12, 42, 32. I want to say that that's 30 degrees Celsius, 30 degrees Celsius, and we do the math. So we're going to get the 226 divided by 58.3 divided by 30. I'm getting a C value, and I'm taking it to 3 sig figs here, 0.129. 129 joules per gram degree Celsius. Okay, there it is. And hopefully that video walking through every single one of those helps. And if not, come to class. We can do some more practice. And I'll see you guys online soon. All right, take care. Bye.